Good morning, everyone. I am Sudeep Reddy, and along with my teammates Divedikshita and Subhashri, I am presenting our project titled Washing Machine Simulator using PICSim 8778, done as a part of the Embedded Systems Internship at EMERTXE. Here is an overview of our presentation. I will walk you through the introduction, objective, tools, project requirement, and what we learn in Embedded C and microcontrollers, up to the type of embedded system in the segment. Introduction. This project stimulates a real-world embedded control system. We use PIC16F877A microcontroller to control outputs like a motor, buzzer, and display based on inputs from switches, just like how washing machine works. Objective: to design and implement a microcontroller-based control system that reads multiple digital inputs and responds by activating appropriate output devices such as buzzer, motor, and status delay. To develop a working embedded system using PIC16F877A microcontroller, demonstrating digital input-output interfacing, peripheral control using embedded C basic automation logic to gain hands-on experience in writing and debugging embedded C code, working with real-time control systems, following a structured project development lifecycle to build a foundation for real-world applications in areas like home automation, industrial machinery, and smart systems. Here are other tools required: MPLAB X IDE PICSim LAB, and X8 compiler. The MPLAB X IDE is an integrated development environment provided by Microchip. It is used to write, build, and debug embedded system C code for PIC microcontrollers. It offers a user-friendly interface, and it is essential for managing source files and viewing compilation outputs. PICSim LAB is an open source simulation tool that allows us to test our code and circuit design virtually. It simulates the hardware environment, including LEDs, buttons, sensors, and the PIC microcontroller itself. This eliminates the need for physical hardware and helps in faster testing and debugging. And the last one, XCA compiler. It is used to compile the C code written in the MPLAB XID. It generates a machine readable .hx file which can be uploaded to a microcontroller or simulator. This compiler is specially designed for 8-bit microcontroller, making it a critical tool for this project requirement. The project followed structures requirement like writing clear specs, designing flowcharts, coding in embedded, and finally documenting the entire workflow, simulating how real embedded product development works. Knowledge on embedded C. What we learn in embedded C. Fundamentals of embedded C: syntax, data types, operators, functions, and modular code structure. Use of if, switch, for, while, and do while for logic control. Manipulating individual bits. Reading digital inputs using GPIO. Writing logic to control buzzer, motor, LED, and displays. Using external internal interrupts for their real-time responsiveness. Generating accurate delay and periodic operations using timers. Identifying syntax and logic errors using step-by-step simulation. Writing structured code. Writing well commented, maintainable, and embedded C code. What we learn in microcontrollers. We learn microcontrollers basics. We understand the internal architecture: CPU, ROM, flash, RAM, input output ports, timers, ADC, and interrupts. Pin configuration functions. Learn how to configure pins as inputs or output and manage port level operations. Peripheral interfacing. Interface switches, buzzers, motors, and displays using GPIO, PWM, and ADC. Register level programming. Access and control hardware features using special function registers. Timers and counters. Used hardware timers for creating delays, counters, and periodic tasks. Interrupts. Implemented external and internal interrupts for responsive time. Microcontroller programming workflow. Followed end-to-end flow. Code to compile. Compile to stimulate or debug. To flash. To test. Basics of embedded C. What is embedded C? A specialized version of C optimized for programming and microcontrollers and embedded systems. Enables direct hardware access while retaining the structure of standard C. Key features: supports hard level operations, memory efficient, suitable for resource constrained devices, allows bitwise operations, interrupt handling, and register level programming. Why we use embedded C? Industry standard for embedded firmware development, supported by popular IDEs like e.g.MPLAB X IAR STM32 Cube IDE, runs on 8-bit, 16-bit, 32-bit microcontrollers. Example: 8051, ARM, AVR, and PIC. Applications: IoT devices, consumer electronics, automotive ECUs, industrial controllers, medical devices, home automation. Embedded systems. What is an embedded system? A special purpose computer system designed to perform one or few dedicated tasks. Integrated into a larger system, combines hardware and software to perform specific functions. Key characteristics: real-time performance, compact in size, highly reliable, low power consumption, uses programming logic to control tasks. Types of embedded systems: standalone embedded system, operates independently without relying on a host system. Example: calculator. Real-time embedded systems respond to inputs within strict time constraints. Example: pacemaker. Networked embedded systems communicate with other systems or networks to perform their function. Mobile embedded system, portable systems with embedded control for mobility and functionality. Applications: automotive, medical, industrial, and consumer.
Hello everyone, I am Subhasiri. I am an Embedded System Intern at EMERTXE, worked on the washing machine simulation. Now I'm going to explain about some of the topics, which is introduction to microcontrollers. What is a microcontroller? A compact integrated circuit that consists processor, memory, input-output peripherals, acts as the brain of the embedded systems. Key features: design for real-time control of electronic devices, operates at low power and it's cost effective, offers an on-chip peripherals like UART, SPI, ITC, PWM, ADC timers. And popular microcontroller families are 8051, AVR, PIC, ARM, Cortex-M, MSP 430, and widely supported by the KL, MPLAB, STM32Cube IDE, etc. Applications of the microcontrollers are home automation, for example, like the smart lights, automotive systems like close control, consumer electronics, for example, microwave ovens, medical devices like the digital thermometers, and this is the PIC 16F879A microcontroller, which used is the this is the microcontroller used in our washing machine project, and this is the block diagram of the PIC F877A microcontroller, and these are the some of the components. A popular 8-bit microcontroller from the microchips PIC 16 family, widely used in embedded system, robotics, automation, and IoT projects. Known for its simplicity, reliability, and rich peripherals. Key features: CPU 8-bit RISC architecture, memory 14 KB flash, 368 bits RAM, 256 bytes EEPROM, input-output ports, 33 general purpose input-output pins, timers, 3 timers, timer 0, timer 1, and timer 2, and analog 8-channel 10-bit ADC, and communication interfaces like the USART, SPI, and I2C. Peripherals: PWM modules for motor control, generate pulse width modulation signals to precisely control devices like the motor and the LEDs. Watchdog timers is self-reset mechanism that restarts the microcontroller if the system hangs on malfunctions. Interrupt support, internal and external, allows the microcontroller to respond immediately to important events without continuously polling. In circuit serial programming supported, enables flashing or updating firmware directly on the circuit board without remaining the microcontrollers. And applications: home automations, sensor data logging, industrial control systems, LED or buzzer control, LCD display interfaces, and robotics projects. This is the block diagram of the washing machine project where these switches SW5, SW6, SW4, SW1 are the inputs of the microcontroller and the display, motor, buzzer are the outputs of the microcontroller. So let's discuss about the input components. SW1, SW4, SW5 and SW4 SW6 are the switches. These are the digital input switches. Each switch represents a specific user control action, like on off mode change. When pressed, the switch sends a high or the low signal to a microcontroller's input. For example, switch 1 could trigger an alert via buzzer. Switch 4 could start or stop a motor. Switch 5 would reset the system. Switch 6 might change the display status. And output components. First is the display. A display output device such as the LCD or 7-segment display shows system information like current mode, switch, status, motor on or off, LS or errors, driven by the microcontrollers through parallel or series interface. Motor. A DC motor or the stepper motor controlled by the signal from the microcontroller could be caused for rotating fans, conveyor belts, or the actuators, typically driven via a motor driver circuit. For example, L29 3D or the relay. Buzzer is sound generating output used for the alerts, warnings, event notifications, controlled by the microcontrollers using a digital output pin. High is on, low is to off. Are the key features of the project. Microcontrol reads the control system using the PIC 16F8778 to control the outputs based on the switches input. Multiple digital inputs supports the multiple switches like switches for real-time control. Multi-output response controls buzzer, motor, and display through logic execution. Embedded C programming implements decision making and peripheral control using the C. Real-time operation, immediate response to user input, ideal for the automation system. SDLC oriented workflow covers the full cycle from requirement to design, design to code, code to test, and test to the document. Applications of the project. Home automation, control lights, fans, alarm based on the button inputs. Industrial control panel operates machines or indicators through the simplified switch logic. Training and education, ideal for learning microcontrollers interfacing and the real-time embedded system logic. Automotive systems simulate button-based dashboard controls.
Hello everyone, I'm Divya Dikshita. I'm doing an embedded system internship at EMERTXE. So during my internship, I worked on a project which is simulation of washing machine. Now I'm going to demonstrate the project using the tools MPLAB and PICSim LAB. So this is the MPLAB where we write our code required for the simulation of the project. So first we need to create a new project. For that we need to go into the file and create new project. After creating a new project, we named it as a washing machine. And here you can see there are some header files and source files. We need to create these files. These are required for the project. Here you can see we created 5 header files and 6 source files. And this washing machine function definition.c. This code consists of the features that we will be seeing on the LCD display during the simulation of the project. Some of the features like daily, heavy, delicates and so on. Here you can also see the water level, auto, low, medium. You can change the features according to your wish. After writing all the codes required for the project, we need to build the project. For that, go to the top and click on this hammer symbol. Here you can see it's built successful and it also created an hex file. This is the hex file. We are going to use this hex file in PICSim LAB to simulate our project. We need to copy this hex file. If we don't get build successful, then there are some errors in our code. If you rectify that, it will get build successful and it generates an hex file. Now let's go to the PICSim lab. So this is the PICSim lab. Here you can see we have used the PIC16F877A microcontroller, and the clock frequency is set to 20 MHz and the LCD display is set to 16:4 ratio. Now we need to load that hex file that is generated in that MPLAB. For that, go to home and this search home, paste that hex file and click on open. So yeah, now we can start our simulation. Here it is saying to press key 5 to power on washing machine. So here we use this LCD display and this is the fan which is a motor and this buzzer to give alerts, and these are the switches RB0, RB1. We consider them like 1, 2, 3, 4, 5 and 6. So now it is saying to press key 5 to power on washing machine. So this is 1, 2, 3, 4 and 5. So now it is powering on washing machine. Here we can see it is showing the washing program, daily, heavy and delicates. If you want to scroll down, just single click on this button. If we want to scroll down, we need to single click on the switch 4. As you can see, it is scrolling down all the features. If you want other features also, we can add in the code. Now I am choosing daily. To change the screen, we need to long press on this switch 4. The code, we have given some delays to the switches so that they know when to function how. Here it is also showing auto, low, medium. Now if you single click, it will scroll down. Slow. Long press on switch 4 and it will change to the next screen. See, here it is saying switch 5 to start and switch 6 to stop. So let's start our simulation. Give a single click on switch 4. It is also showing the time, how much our simulation will take. And if we press on switch 1, it will give an alert that the door is open, please close door, and the buzzer is also ringing. That means it is giving an alert. If we press switch 6, then it will pause. And if we want to resume, we need to press switch 5 again, which is RB4. And the buzzer is again giving alert that the simulation is completed. We need to remove the clothes. And the program again started. So this is how we do the simulation of the washing machine using the PICSim lab. So to conclude our project, through this internship, I gained hands-on experience in embedded systems, bringing the gap between academic knowledge and practical skills. I learned how to write efficient code using EMERTXE and how to interface with real-world hardware like switches, sensors, buzzers, motors, and displays. I also learned how to understand and implement microcontroller-based system design and how to follow the complete project development lifecycle like requirement, design, code, test, and debug. And this experience has strengthened my understanding of microcontroller architectures like PIC and embedded development tools like MPLAB, simulators, and debugging methods. The internship helped build my problem solving, documentation, and presentation skills, essential for both industry and higher education. Now I feel more confident and well prepared for opportunities in embedded systems, IoT, and core electronic domains. Thank you.